Well, good afternoon, everyone. I'm Jason Gibson, CCO at IACMI, the Composites Institute. Innovation Insights is our monthly webinar series highlighting the people, the ideas, and the partnerships driving advances in composites and manufacturing across the U.S. As part of the Manufacturing USA Network, IACMI leads national efforts to scale new materials, to develop sustainable processes, and strengthen U.S. manufacturing competitiveness. At IACMI, our mission is to convene, connect, and catalyze. We convene the composites community to share ideas and opportunities, to connect industry, academia, and national labs, and catalyze real progress through collaboration and commercialization. Today's Innovation Insights reflects that mission, highlighting new ideas, technologies, and applications driving the future of composites. For those new to IACMI, we accelerate composite innovation to strengthen U.S. manufacturing and workforce competitiveness through co-funded projects and access to world-class facilities and a powerful national network. So if you're listening today and you're not currently an IACMI member, we encourage you to consider the value of joining. When you join, you'll be part of a network that brings together peers from industry, academia, and government, all collaborating through our working groups to shape where composites innovation is headed. Whether you're a startup, an OEM, or a supplier, there's real opportunity to get involved and make an impact. We'd love to have you join us. So please visit our website and reach out to us by filling out the online form. And if this is your first time attending, we encourage you to explore past episodes that are available on our website. Since its launch, the series has brought together a wide range of members and partners, each sharing real-world applications, technical advancements, and valuable lessons learned. Our goal is not only to keep you informed on the latest trends in composites and advanced manufacturing, but also to provide a direct connection to thought leaders and innovators who are shaping the future of this field. And today is a good example of that, so let me introduce our speakers for today. Today's Innovation Insights session brings together three leading voices in advanced materials and manufacturing, each addressing a critical dimension of how composite technologies are transforming industry. We'll begin by exploring new manufacturing paradigms that make ultra-lightweight structures possible at production scale. Then we'll move into digital quality assurance, showing how AI and optical metrology are redefining real-time process control. And we'll conclude with a look ahead at advanced carbon materials from recycling standards to the future promise of graphene-enhanced composites. But we'll begin today with Dr. Evangelos Zympeloudis, who holds a PhD in advanced composites manufacturing from the University of Bristol, and he's the founder and CEO of iCOMAT, a company leading the next generation of fiber-steered composite structures. In his talk, Dr. Zympeloudis will present how iCOMAT's defect-free fiber steering process delivers the world's lightest structures for defense and aerospace, achieving structural efficiencies unattainable with conventional layup methods. He'll discuss how this breakthrough allows 10 times faster production at significantly lower cost, creating a new benchmark for scalable, high-rate composite manufacturing. Next, John Tyson, who's the president and founder of Trilion Quality Systems, will present. John is a pioneer in optical metrology with over 35 years of experience in laser-based and digital inspection methods. His innovations covering holography, shearography, digital image correlation, and thermography has supported programs from the B-2 bomber and space shuttle to Blue Origin and SpaceX. John's presentation will explore how digital optical metrology and AI-driven analytics enable real-time quality monitoring and in-situ non-destructive evaluation for composite manufacturing. He'll show how these systems not only enhance accuracy and reliability, but also reduce cost and rework, bringing aerospace-level precision into rapid manufacturing environments. And then to close us out, Terrence Barkin will present. He's the founder of the Graphene Council, which is now expanded as the Advanced Carbons Council. They represent more than 40,000 professionals across the world. His organization leads efforts in standards, quality verification, and sustainability for advanced carbon materials. In this session, Terrence will highlight two pivotal trends shaping the carbon ecosystem: the emergence of reclamation and repurposing standards for end-of-life carbon fiber materials, anchored by a new draft ISO standard, and the evolving graphene market, where supply, cost, and regulatory constraints continue to influence adoption. He'll share how these developments converge to enable more sustainable and higher performing carbon composites for next generation applications. So with that, I'd like to turn it over to Dr. Evangelos Zympeloudis so he can present his presentation. Evangelos?
Many thanks, Jason. So let me share my screen.
Yep.
All good? Shows up?
Shows
Perfect.
up good.
Okay. Brilliant, brilliant. So many thanks for the introduction, Jason. And hello, everyone. My name is Evangelos. I'm the CEO and founder of iCOMAT. The whole mission at iCOMAT is really to deliver the world's lightest structures, but also to solve some of the long-standing problems around composites manufacturing, namely around the high cost and the manual process, to really automate how we produce these structures and enable hyperscale and low cost. We all know why we need lightweighting, especially for anything that flies, whether that's a missile or a plane. Weight is really the enemy, directly affects payload and fuel burn. And the trend in the industry has been very clear in replacing metallic components with composites, to the point where all the new products in the market are almost exclusively made out of carbon fiber. So there's not a lot really left to replace, and what we need is the next generation of lightweight materials to enable further weight saving. And that's what we can deliver with iCOMAT. And we can do so for the entire structural stack across defense and civil aviation. So anything from the wings of a fighter jet to interstages of commercial launchers. And the way we do this is really by going back to the basics with carbon fiber and composites. So again, as we all know, every composite part starts life as a textiles. So composites are made of millions of very strong fibers. And really the peculiarity with these materials is that they are only strong in the direction of the fibers. So the way we design and manufacture today to really compensate for this is by stacking straight fiber layers at different orientations, and this gives us roughly the same strength in the key directions. But the structure is never loaded the same in the key directions, so you end up placing a lot more material than you actually need. And it actually would be far more efficient if you could steer the fibers, and in such a way you could reinforce a structure only in the critical areas. And this could give us components which are not only lighter and perform better, but also require significantly less raw material, so they are cheaper and they are faster to produce. So this whole idea, this concept, got known as fiber steering in our industry. It was originally proposed by NASA in the late 80s, and there's quite a big body of literature on why fiber steering is better and why we should be designing and manufacturing composites like this. But the big bottleneck always has been manufacturing. So it's pretty much impossible to fiber steer with existing technologies, at least without generating severe defects, like the ones that you see in these images. So what we have developed at iCOMAT, it's the world's first and only technology and process that can actually fiber steer without any defects at all. So you see here our generation 1 system, steering 4 inches wide, aerospace grade prepreg. This technology is based on 10 years of academic R&D at the University of Bristol, and then 6 years of industrialization at iCOMAT. And as you can see from the close-ups, really the quality is excellent. For those of you that work with AFP, the difference with our process, aside from individual tapes, is that you can also place one tape next to the other steer tape, that is, without any gaps or overlaps. Again, something that is not possible with existing processes. So all in all, this is the world's first technology that can actually produce defect-free fiber steered parts. And what you see here is a generation 4 tape length system. So this is our latest machine. So we released this about 2 weeks ago. And what you see here is straight line deposition at 1 meter a second. And fiber steering demo will follow. Now I have to stress, because with our process we have to effectively modify the tape to steer its fiber path, and we do this by using shear deformation. Every subsystem of the head had to be developed to an extreme level. To give you an idea in terms of heating, it's the only tape length system in the world that uses an infrared LED heating array, so about 150 individual LEDs, and this gives us tremendous control over the temperature profile. So what you see here is quite phenomenal, actually. It's steering at 0.7 meters a second, and the radii that you see are less than 200 millimeters. So it's orders of magnitude faster and tighter steering compared to an AFP, and is absolutely defect-free. So why does this matter? There are two really good reasons. The first one is structural efficiency. By placing the fibers directly on the load path, we can drastically reduce the weight of structures. And it's best to illustrate this with an example. So what you see here is work we did with Airbus MBA on a program many years ago. So it's the lower wing skin of an airplane. You've got what is known as the manhole plank. So literally a man has to crawl through these holes to really inspect the fuel tanks and the internal structures. But the wing is loaded in bending, so you really want the fibers running straight across the length of the wing. But you've got all these holes and you're effectively cutting the fibers. So that creates a huge stress consideration. Now, it's not hard to imagine what we're doing with steering. So we're effectively steering the fibers around the hole to eliminate that stress concentration. And that allows for a drastic weight reduction. So we're talking 65%, and that's using the same raw material that's used in production today. So they liked it so much, they said, okay, can we try to replicate that design with existing fiber placement systems that we use today? And the result is what you see on the bottom left-hand side of the slide. It's full of localized buckling and wrinkling, which are localized defects that not only reduce performance, but they also make it almost impossible to certify. And these are some of the results. So with our technology, which is RTS, which stands for rapid tape shearing, we're able to achieve 3 times the load to mass ratio compared to the QI laminate that's flying today. And we've done a lot of work also on similar structures for space, which was one of the very first applications of fiber steering. And we've recently produced and tested the world's first fiber steered cylinder that outperformed the best straight fiber design. The benefits were very well documented in the literature, but nobody could realize them in a test result because of the defects that you get when you manufacture fiber steel structures, which you see here. But we actually did a defect-free cylinder. We achieved 24% higher buckling load, which translated in about 20% weight reduction. And crucially, we massively improved the reliability load by 300%. So I won't get too technical, but effectively, this is a key measure in space structures, which determines how sensitive is the structure to imperfections or damage. So effectively, it's a much safer way to design with steering because you know exactly how the load travels through the structure. Now, the second advantage of steering, and probably this is even more important, is that with this technology, you can really unlock industrial production rates with composites really for the first time. And the way we do this is by leveraging a workflow that's been used in automotive. It's not new, but it's been used in automotive for decades. So the way we make cars today is by stamping or forming. So we take sheets of metal, we put them in a press, and off comes a component. And this works really well with metal because metals can stretch in all directions, but carbon fiber doesn't stretch. So if you try to form anything complex, like the fuselage of a fighter jet, it really is like taking a piece of paper and trying to wrap it around a football. It will create lots of wrinkles. So what we do is we use software, we predict where those wrinkles are, and then we pre-steer the fibers in 2D so that you can stamp form the component in 3D without any defects. So we can effectively engineer stretch into the 2D preform. And that allows you to produce many times faster. So again, best to illustrate this with a couple of examples. So the first one is a fuselage frame. So this is, or a curved beam. It's a representative geometry that's widely found in civil and defense aviation. You've got about 900 beams like this reinforcing the fuselage of a commercial airplane, and you've got many curved beams in the wings from spars and stringers reinforcing the wings. So effectively what we did here is we didn't change the design. So on the final 3D part, it's the existing QI design that's flying today, because that was one of the requirements of this project. But what we did is we took that plybook and from a 3D geometry, we projected it into 2D. And then you will see here that pretty much every single orientation required a degree of steering. And that happens because this is a doubly curved shape. So when you try to form it, the fibers are moving. So we're pre-steering in 2D so that the fibers end up in the correct place on the 3D. So once we do this, then we use our CAM software and we program the machine, and then we let it run. And in this case, it did about 21 layers all in one go. And also what you will notice is that we have nested multiple frames together. So this preform here can do about 3 fuselage frames. Then we ply cut its preform, and then in this case, we use the hot drape forming system. And the result is a defect-free beam that you see here. Now, if you try the same workflow with a straight fiber preform, everything is the same. Material, forming system, mold, everything the same. The only thing we change is instead of a fiber steer preform, we started with a QI preform. And this could be the result. It would be full of localized wrinkling and buckling, which are these, defects I mentioned previously. So this workflow that you saw, is really not possible today. So one of the most common ways of manufacturing these frames is using direct 3D AFP. And the issue is, if I freeze here, you see there is a lot of localized buckling as you move from one face to the other, irregular gaps, which effectively, to certify the structures, the most common way is to add about 30% more material to improve the allowables. But aside from that, added weight and waste, it's also very slow. It takes about 8.5 hours to do 21 layers using this system. So if we use our lay, flat, and form approach while using very wide tapes, so we're talking 8 inches wide, then we can do the layup for one frame in about 5.2 minutes. So this is really going from 8.5 hours to 5.2 minutes. Here you have defects, here you have no defects. So we're not talking about, a 2% improvement here. This is an order of magnitude improvement in terms of production rate and also cost. Another quick example, this time is from the rear fuselage of a fighter jet. Same approach. We do the design, then we run a forming simulation, we do the flat stack, and in this case, we use a stamping system. So this is a heated press, so you cure while you press at the same time, and really it's beautiful. It's lighter, it's cheaper, and we literally made this 10 times faster compared to the nearest technology. So where are we going with all of this? Really, the vision here is to create the world's first lights out factory for composites. We're not there yet, but we have all the necessary building blocks now. And there are two main streams. The first is the hardware. And I believe we're the only manufacturer in the world that makes their own tape laying systems in-house. This is a key part of our technology stack. And it's the only tape laying system that can fiber steer, which makes all of this possible. And then everything else we buy commercial off the shelf. And we also have a dedicated software team that creates what we call an end-to-end digital thread that connects the CAD from finite element software to forming simulation to the programming of the machines. So we developed our first factory, which is in the UK. We call this Factory 1. We did this in really no time. It took us 7 months from the moment we signed the lease. And it's 45,000 square feet and it has end-to-end capability. So you can literally go from the raw material and now it comes a finished component. And I'll just give you now a quick preview of the capabilities. So as I said, we have a design and software team, so we can do pretty much any design step that is needed from the initial CAD all the way to having the machines programmed. We have slitting capability, so we can take the initial parent roll and slit it to narrow widths that can fit into our tape laying systems. We have the capability to do tooling, whether it's metalling or composite. We have multiple tape laying systems, so there are about 4 tape laying systems that are live at the factory, and they're all fabricated in-house. And this will soon be 6. 2 large autoclaves, 2 presses, a hot drape forming system, a lot of inspection capabilities, and we even have a paint booth. And lastly, a very large clean room that can also do manual laminating. So as I said, the whole idea here is that we have complete end-to-end capabilities, from the raw material to a finished component, painted and inspected. I'll just give you a very quick preview of how this could work for, let's say, the production of a drone wing. So after the initial optimization, we program the machine and then we let it run. And in this case, it did 11 layers only one go. Then we use a ply cutter to create a near net shape preform, laser projection to effectively align it on the mold, and then we cure it in the autoclave. So all these steps, aside from obviously moving the preform from one station to another, don't require manual intervention. And really, that's the workflow that we want to refine to create, as I said, the lights out factory. So this is a quick preview of our technology and our capabilities. In terms of the company and its size, so we're about 80 people now. We've got an R&D center in Bristol and our factories in Gloucester, and a software team in Athens. And we're in the process of setting up our initial facility in the US. So all this was made possible by a funding round that we completed last year. That was our Series A, and it was actually the largest Series A ever in composites. It was led by a US fund called 8VC, and it was actually the first direct investment of NATO into a private business. We will be raising again, which is going to be early next year, and with Series B. Really, our main aim is to set up Factory 2, which will have the latest generation of the iCOMAT systems and will take us all the way to a lights out factory. Yeah, so this was a quick presentation on iCOMAT. I think, Jason, we have now time for some questions, if there are any.
Yeah, quick question for you. Is this applicable to both thermosets and thermoplastics? And can you speak a little bit to the types of materials you worked with?
Yeah. So at the moment, we're working primarily with thermosets and dry fiber. We have worked with thermoplastics, mainly some systems by Victrex, which are relatively low melt for thermoplastics. The technology is applicable for thermoplastics, but we haven't developed a dedicated head for it. So we're focusing on thermosets and dry fiber, and there is the potential for thermoplastics.
Great, thank you. Appreciate that. And in the interest of time, let's go ahead and move on to John Tyson to talk about Trilion and his capabilities. So if you wouldn't mind, stop sharing there, Evangelos, and then go ahead and take over.
Well, thank you very much, Jason. And Evangelos, great presentation. Let me share my screen. And hopefully people can see that.
Yep, we could see it. It looks great.
Okay, good. I wanted to talk about our optical metrology technologies utilizing AI to do digital measurements of materials, structures, processes to really bring quality upstream in the process of manufacturing, really making manufacturing substantially more efficient and less rework, scrap and defects and that kind of thing, and making better quality parts as we move forward, and applicable to all composite workers. Thank you, IACMI, for putting this on and allowing us to present on this. So Trilion has been in the industry for more than 27 years now, and this is our headquarters in Philadelphia, but we have offices around the country, and we also do workshops all around the country too. Doing not only providing our systems, but doing engineering services to support our customers in the implementation and training, ongoing training, all that kind of thing. And we're teamed with Carl Zeiss, and people may know the GOM products for all that time period. Just simply, on strain gauges, Boeing had a concern that strain gauges were costing too much. And so engineering reported back to the VP, him saying, find a better way, that our Aramis technology is 10 times cheaper than mechanical gauges, 50 times manpower savings and schedule savings. And really 100 times better data, mainly because we're seeing full field. And the idea that composites, if you're not seeing full field, you don't really understand your composites, is sort of crucial to next generation aircraft. Also at General Motors, we're doing stamping operations, looking at formability of materials, everything from steels and aluminums to composites. And at General Motors in their stamping operations, we're saving them $100 million a year, literally transforming how they do business and moving quality upstream. They're really key to their operations. So we have a couple of different technologies we work with. Core is our Aramis optical strain measurement tools, where we can see the deformation and strain in the materials, and again, full field holistically. We also have scanning methods with a laser scanner and a white light scanner, looking at the overall shape of components, making sure they are matching to CAD as during the building process and that kind of thing. Our tri-top gives us coordinate system and global displacement and positioning of things. And SUPAR gives us this augmented reality in being able to do interactive inspections on components and structures. We couple Aramis with high-speed cameras to look at drop tower manufacturing operations and all that kind of thing, high-speed events, and thermography to bring the temperature profile in, which leads us into manufacturing operations and looking at the formability of components, the layup of composites, and that kind of thing. Coupling all of this is our engineering services, and hence our local offices around the country and around the world, really. Where our engineering services are crucial to integration of these tools, keeping people trained, and keeping advanced applications being further developed, keeping us on the cutting edge. And we also have our automation suite of technology, which automates all of these tools. And this allows us to then make these fully integrated into your manufacturing process in really nice ways. So key to our business model is moving quality upstream. And so how do we improve your quality earlier on so there's less problems downstream? And this is really digital manufacturing. So looking initially at materials, your material properties, materials are core to everything we do in manufacturing and core to all new generation products, that kind of thing. Then understanding your processes and components, being able to do in situ monitoring, that kind of thing, understanding your assemblies during the manufacturing process, giving guidance during the manufacturing, structural testing, as really understanding that you're producing good products out the door, and maintaining the product through its lifetime are some of the key things we're working on. So our Aramis optical strain is considered this full field optical capability. We're measuring 3D shape, deformations, and strains. We're now a certifiable measurement to ASTM E83. So this becomes just a very nice tool for understanding composites in general. So when it comes to material testing, we've had some breakthrough steps doing this full field measurement. Our equipment's now sort of plug and play, long-term stability, all that kind of thing. We have this measurement certification to E83. We're using etching, our automated etching methods for patterning, automated patterning for a difficulty in sometimes. And then the automated templates allowing us to automatically make the measurement. So it's really a plug and play system. We also have our new AI sensor, which allows us to do real-time measurement and in material testing, get axial and tensile strains, just replacing analog gauges with full field of optical methods that give you much better understanding of your material properties, and hence a lot less testing and a lot higher quality data. When you're dealing with materials, even composites particularly, but even in metals and everything else, there's much more happening than a clip gauge or a strain gauge is showing you. So we're giving you automated stress strain curve, all your material testing parameters, and NASA Glenn stated that Aramis is the most consistent material properties of any method. So, getting these material properties is just really crucial to, the beginning of your processes, but then doing in situ NDE, monitoring the quality while you're building your product, final inspections, alignment and digital measurements, final structural testing, and then structural health monitoring in the future. So this process of monitoring your processes all the way through the manufacturing process and moving quality upstream, which is providing higher quality and more manufacturing efficiency. This getting full field measurements, getting your material properties, in situ NDE, we'll talk about in just a moment, as built quality, and doing final inspections in three-dimensional space rather than 2D space. Really provides a much better measurement of your all the way through your processes. And then we can add structural health monitoring for lifelong monitoring of your components and structures. Engineering services are key to our business. We support a lot of customers all over the country and the world, and really understanding how advanced processes are working. One application was developing our Aramis thermography back in 2006, where we coupled the thermal camera with the Aramis to measure not only full field deformation and strain, but the temperature change during the same thing, and using that to calculate thermal expansion and using that to correct strains to get the true mechanical strains in it. We then applied this to in situ monitoring during composite layup. And so here we are monitoring the layup of the build, fiber alignment to CAD, FOD detection, looking at voids and FOD inside the structure. So backing material and things like that, which are the bane of composites layup, we can be detecting this in real time, and fuzzballs and all that kind of stuff. And so be able to make sure you have build quality assurance while you're building, and this full field NDE, and documenting all of this in real time. We get into initially fiber alignment. We can see the fibers themselves in the measurement locally and globally, and comparing that to CAD. And we can also do defect maps of, laps and gaps, FOD, voids, all that kind of thing, fully documented on the builds while you were building them. And be able to give you a list for the quality manager then to accept and reject any of these. And we're doing this in real time, so you can be fixing the problems in real time while you're building the parts. And so we can also do this in hand layup. So we're doing the hand layup guidance, fiber placement, fiber alignment, FOD detection, all critical, and getting this quality assurance while you're building your part, and documenting all of this in your quality control systems. We can also do scanning. In this case, we're doing scanning thermography, and we're looking at this composite structure and seeing the bond lines all the way through, in this case, the trailing edge, leading edge, spar, all very rapidly, and typically with the same equipment that you've been doing the other measurements with. We can also do structural testing. This is our, structural testing at most of the big aerospace companies are done at their facility, but we also offer engineering services out in the field or at your customer site. In this case, we're doing it at Wright-Patterson Air Force Base, one of the original structural test facilities. Here we are looking at Joby's V-tail with a bunch of Aramis equipment, and monitoring key areas or the entire structure, as the case may be, for your customer. So monitoring this transparent manufacturing, through the process of from materials to in situ monitoring to inspections to guidance during builds, doing full field optical, precision alignments, everything from regular structures to click bonds, all these kinds of things, drilling operations, all optically guided, documented in a precision way, and really speeding guidance, tooling, speeding the manufacturing process and reducing tooling costs. Then structural testing, and then structural health monitoring, all key areas in this transparent manufacturing process. So this gives you, assured quality for rapid manufacturing, certified materials, in situ monitoring, AI-driven defect detection, and rapid scanning with our thermography technology for in situ monitoring as well as NDT. We end up with this multi-scale quality monitoring all the way through your process with really closed loop control and monitoring the quality as you're building and moving quality upstream. And then we can do life cycle assurance of these structures also in the field. So this is my presentation, and I thank you all very much. And any questions or thoughts?
Well, thanks, John. That's very good. Couple questions for you. For the AI involvement in the in situ closed loop type training, there's got to be some type of training involved to the AI. Can you give us a feel for how long that takes, how many data points, just kind of a gauge around that?
Yeah, it's amazing. AI is really just amazing. It compresses reality. And so when it, we do, we've been training our models for years, and and it's just become more and more powerful. But finding a defect is sort of easy for an operator to see a defect, and it's also easy for AI to find the defect. But we're getting to the point where we're now measuring the shape of a component, the imaging of the component, the thermal response of the component, and accommodated calculations using all that data. And no operator can see all of that information at the same time, but AI can see it all at the same time. And so it ends up being really, really powerful. And our models are always improving, but because we've compressed reality to finding defects and measuring various other parameters, that they require a substantial amount of training, but they're using the same models for all our methods, and they are getting better, and we can train on specific applications, but the models are pretty broad-based. They're really pretty powerful.
Great. Well, thank you very much for your presentation.
Thank you all
right,
very
if
much.
you wouldn't mind stop sharing, and then Terrence, we'll go ahead and turn it over to you.
Thank you, Jason. I really appreciate the chance to be with everybody here today, and look forward to speaking with you. Let me just bring this up. There we go. Can you see the presentation?
I can. It looks good.
Okay, I think start at the front. Well, again, thank you for having the Advanced Carbon Council participate here. As Jason, as you said at the beginning, we started as the Graphene Council back in 2013, so we've been at this now for well over a decade. The Advanced Carbon Council is a global trade association, so that means we have companies that are members, and then we have individual subscribers that get our advanced carbon intelligence briefings on a variety of materials, which I'll describe here very shortly. But we reach more than 40,000 materials professionals that are working with advanced carbons, either producing them, researching them, developing applications, or using them in different applications. So from our perspective, when we talk about advanced carbon materials, we're talking about everything you see here on the screen that includes nanomaterials like carbon nanotubes, graphene, and other allotropes of carbon, nanodiamonds, but also the macro forms such as carbon-carbon composites and carbon fiber, synthetic and engineered graphite, etc. So it's really the full spectrum. It's maybe easier to describe what we don't cover, and that would be things like natural flake graphite or petroleum-derived carbon black materials, unless it's a recovered, recycled material. So we cover this full spectrum, and we do that because there's a lot of synergy between these different carbon materials. The one I'd like to focus on first is going to be on graphene. And often when people hear the term graphene, they may not be entirely familiar with the fact that this is more like a family of materials rather than a singular specific material. Graphene can include sp2 bonded carbon that's in a single layer up to 10 carbon layers. And that you have an example on the left of a few layer graphene platelet. There's also a material referred to as graphene oxide, which has a high percentage of oxygen content, 30 to as much as 40% oxygen, which changes the behavior of the material significantly. Graphene, of course, is noted because it's highly electrically conductive, but graphene oxide is an electrical insulator because of the oxygen. And there are many different ways of making graphene, not just from graphite as a feedstock, but increasingly graphene is being made, for example, from folks that are producing hydrogen from a gas, taking methane, or you can take oxygen and acetylene and create graphene out of that. So using gas precursors results in a form of turbostratic or disordered flakes of graphene. And then lastly, you also have amorphous carbon, which is not graphene, but depending on the optical spectroscopy or microscopy, it might look like a graphene material, but it's important to distinguish the differences. And then in the TM images below, you can see the difference in particular, where we can get right down to the level where you can actually count the individual carbon layers. Now, I wanted to bring this up because there's been a lot of discussion about graphene over the years and about all the promise of it. In particular, the fact that graphene is highly electrically conductive, highly thermally conductive, extremely strong, provides UV protection, provides strong barrier properties, means that this one material can be used in many different ways for different characteristics. So exploiting either the electrical conductivity or the thermal conductivity in a given application means that it can be applied across a really wide range of applications. That's the exciting part. The challenge has been, as a relatively new material, that it's been perceived as being prohibitively expensive to use. So that was the number one barrier in many cases. You would have heard early press releases about this costing, $100,000 a kilo or something crazy like that. So cost has been an issue. The ability to scale at the levels that are needed to use it in a commercial scale or industrial scale has been an obstacle. And the other one, because this is a nanomaterial, at least in the United States, it's regulated under TSCA, EPA and TSCA regulations. In Europe, it's under REACH regulations. These three factors, the perceived cost of the material, the primarily being produced by small scale or startup companies, so not really at an industrial scale, and the regulatory burdens have been the primary reasons why graphene has not been deployed extensively to date. And what I'd like to say is at this stage in 2025, all three of these obstacles are being addressed, and commercialization of this material is now taking place. If we look at pricing, because graphene is this family of materials, you have to kind of compare apples with apples. So making a true single atomic layer of graphene results in one type of material with a certain type of cost basis, and it's also more suited for specific applications like sensors or electronics. And then as you add layers of carbon up to 7, 8, 9, 10 layers of carbon, then you have different types of applications, more mechanical properties, and the cost comes down. I would say that the pricing for graphene is extremely volume dependent. So there's a huge difference between buying a gram, a kilo, or a ton of the material. But the real important aspect to understand, in almost every case, graphene is not used by itself. It's used as an additive for another component. And this is especially true in the case of composites, where graphene might be in the resin system and is used at a fraction of a percent. And so ultimately what people need to understand and look at is not the cost on a per unit basis for the graphene, but what does it cost to put graphene into your system to get an improved level of tensile or flexural or impact resistance in terms of strength for the component that you're adding it to. And you could have two different types of graphene, one of which you might be using 1/10 of the other. And therefore, then you have a tremendous impact on what your actual end use cost is as used. Where we're at today with graphene, it is a very cost-effective additive to be used in composites and can be less than some of the resin systems in terms of cost and what it can replace. If we look at volume, there are more than 200 companies today that make graphene, and of those, there is a handful of companies that make it at extremely high scale and very repeatable. Now, the good news about graphene production, there are no bottlenecks or constraints on the raw materials that are needed. There are a dozen different ways of making it, so you don't have a technology constraint where one particular company dominates or has a throttle on production methodology. And so the constraints from that side on production are just not there. In this really relatively low capex to set up a graphene production facility. So right now the obstacles in terms of large scale production are not there, other than a bit of capital and then the demand signals coming from end users. The really important one that has been an important constraint and a significant constraint, but is being addressed, is on the regulatory approval side. Because graphene is a nanomaterial, it is regulated by EPA under the TSCA regulations in the United States and under the REACH consortia or the REACH regulations in Europe. In Europe, there has been a consortia of companies that have gone through the REACH approval process. And so graphene, and that means the entire family of graphene materials, have been approved for use in Europe, which gives a distinct advantage to enterprises and manufacturers in that jurisdiction. And in the United States, the approach has been each company registering their materials one by one, but we've had recent announcements, and there will be more coming, of companies who have obtained their REACH, or rather their TSCA approval for material to be commercialized and used in the United States. So if you add the cost component, the scaling constraint, and the regulatory approval, all three of these important obstacles to full commercialization are being addressed and tackled at this time, which is a big signal for end users to revisit looking at graphene as a material to make next generation, lighter, stronger, better composite materials. And we are here to help with that. The second topic that I wanted to talk about is the great interest and movement in reclaimed or recycled carbon fiber materials. There's a lack of consistent nomenclature around what is meant by reclaimed or recycled carbon fiber. If we look to ISO for a definition on recycled material, there's pre-consumer material and post-consumer material. If we look at the panorama of reclaimed carbon fiber material, there's quite a bit of variation, and we can look at that from three aspects here. One is the source of these reclaimed fiber materials. So there is a significant stream of material that's coming directly from virgin carbon fiber producers for material that is off spec. Now, this just might be a box of spaghetti, or this might be material that's actually on spools, but it didn't meet spec, and therefore it can't be used in their normal sales process, and it gets diverted into the reclaimed, recycled sector. Then you've got production scraps from facilities making composite parts, and these are the offcuts from the patterns that are not usable. Those are production scraps. And then we have material, for example, end of life windmill spars, where the materials are being reclaimed. And then we can look at these different processes for reclamation. So you have things like mechanical separation, chopping or milling of the reclaimed fibers. And in the case of reclaimed CFRP product, you might have a pyrolysis method that's applied to remove the resin and liberate the fiber, or a solvolysis process, chemical process, to dissolve the resins and again to get at the fibers. And then what we're left with in the reclaimed or recycled, repurposed carbon fiber materials is a really broad format. This is just the physical presentation of the materials, but then you have within that a wide variety of the actual performance characteristics or strength characteristics of the fiber, because it's many grades that you're starting with, many different ways of treating it, and then they end up as some short strand fibers chopped, milled into a dust or a powder, pelletized, and then non-woven reclaimed carbon fiber product. What we have seen is that there is tremendous interest and latent demand for reclaimed carbon fiber materials, but one of the biggest obstacles is the lack of consistency or standards for grading systems for the reclaimed or repurposed carbon fiber. There is at this time an ISO draft standard. The ISO DIS 19374 is a draft standard that is within the ISO system, and it does have a proposed system for assigning numbers and grades and categories to some of these reclaimed fibers. However, when we look at it, that standard, which was developed by we understand a consortium of 3 virgin manufacturers, has not adequately taken into account the full breadth and depth of the reclaimed, recycled carbon fiber sector, and nor has there been enough input from stakeholders who are in that business. And there are new companies every day emerging that are working on how to develop a high quality, consistent, reclaimed, repurposed carbon fiber product. So as the trade association working on standards for these particular materials, this is an open invitation to anyone who has an interest in this topic to work with us on a volunteer task force to help make sure that the standards that eventually are approved meet the needs of the entire stakeholder community, and in particular for the end users and the potential purchasers of reclaimed, recycled fiber. And so we have a task force for those standards. We're also working on standards for graphene with ASTM. We did get a standard approved through ISO for graphene classification, and the next step is an ASTM numbering system. There are new standards for carbon nanotubes, or rather existing standards for carbon nanotubes that are under revision. I mentioned the reclaimed carbon fiber, carbon nanofibers, biochar, and Maxine's an emerging carbide nanomaterial. These are all the standards projects that we're working on at the moment. And with that, I'm keeping my presentation really concise and short, just to share updates on those 2 things. The summary is that graphene has overcome the main hurdles of price, scale, and regulatory obstacles to be available to be commercially implemented, and holds great promise, in particular for composites, to help make them stronger, lighter, and longer lasting, as well as more recyclable. And for the carbon fiber sector, it is really important, even for the virgin carbon fiber producers, that there is a good end of life pathway for carbon fiber materials. I think that's true for any user of carbon fiber or anybody who has an interest in this sector, is that having a good end of life pathway, which includes transparent, usable standards for grading and classifying those different second life materials is important, and we would like to get everybody's input for that. And with that, Jason, I'm going to hand back over to you. I'm going to keep this short today.
Well, thank you. I appreciate that. Great presentation. Sounds like you guys are doing a lot in the standardization world. You mentioned the current ISO standard for recycled carbon fibers doesn't really reflect the broad range of products out there. If you were to ask for the most support, like where do you need the most help on to get industry involvement to make sure it's reflective of the broad range of different recycled carbon fibers? Is there particular types of companies or suppliers you're looking to gain into that world?
Yeah, that's a great question. I think obviously because of the higher specs in the aerospace sector, I think aerospace is going to be a little bit trickier. But for the automotive sector, for example, there's a tremendous interest to get a higher percentage of recycled content. And the problem there is, how do you get enough material that's of a certain repeatable grade? So I think those in the automotive sector who would like to use more reclaimed recycled carbon fiber are important. There's a whole segment of companies whose business is to make reclaimed recycled, and there's some really great innovative. So this is an emerging sector. Virgin carbon fiber producers have a vested interest in making sure there's a good end use market for this. So they also have an interest. And so we want to see from all of the stakeholder groups what their interest is, so that we have a system that works for each component of that supply chain. I don't know if that answered your question, but that's what we see.
It does. It does. Thank you very much. So I want to thank everybody's time for today. I want to talk
Jason?
about how, oh, go ahead.
Sorry to interrupt. There's a couple of questions in the Q&A, and I don't know if you can see those.
I can't. Go ahead and throw them out.
First, we have one for, I think we probably have time for both of these if we're quick. Joe Fox had a question for Terrence. Which graphene supplier has the largest capacity right now?
The largest capacity for graphene production is a company called Nano Explorer based out of Canada. That's 4,000 metric tons a year. We have additional capacity coming online almost from all of the other producers, companies like Levidian, Hydrograph, companies like that. Have quite a good amount of capacity. So we're looking at right now, I think 25,000 metric tons per annum on the capacity side for graphene production.
Thanks. And I think we have time for one more. This was for John Tyson. Sorry, John, I didn't catch this one in time, but Dale Brocious was asking, have you had success in detecting kissing bonds in composite structures?
Right. So this is sort of a key parameter in a lot of manufacturing builds, is being able to find kissing bonds. And obviously, when you get into building composites, something like backing material and other foreign objects create these kissing bonds. But also you end up with certain levels of porosity that create it also. These are all measurable events that can be found while you're building or less pleasantly after you've built the part. It's kissing bonds have been the bane of existence for NDT for a very long time. But the thermal results on it actually are one of the best methods for doing kissing bond measurements.
Great.
Thanks.
Just a quick note on carbon nanotubes and other carbon stuff is when you're adding this to your materials, you need to make sure that you're utilizing it fully and appropriately, and our equipment can see that also. So.
Oh, nice. Well, I want to thank everybody for their time and the presentations today. I want to remind everybody the Innovation Insights we do every third Monday of every month. The next one is November 17th, then December 15th, and then January 19th. So please feel free to register for the upcoming ones. And we appreciate your time, and everyone have a great Monday. Thank you.
Thank you very much, Jason.
Thank you, Jason. Take care.
Thank you.